A company has data. That is the whole problem. It sounds like something that should have been solved once in the 70s and stayed solved. It was not. In 60 years, we have rebuilt the way companies store data 4 separate times: database, warehouse, lakehouse. And right now, a company will happily pay Databricks a fortune to do something Postgres would do on a laptop. That is not stupidity. Each of those 4 generations was born to fix one specific thing the one before it could not do. Once you know what broke, the timeline stops being buzzwords and becomes a single argument. So we are going to walk it, from the file cabinet to the lakehouse, in order with the dates. And by the end, you will be able to answer the question that started this for me. Is S3 a data lake? Let's begin in 1960.
Before 1970, data lived in files. If you wanted the customers, you opened the customer file. The program reading it had to know the exact byte layout of every record. Change the layout, and every program that touched it broke. So IBM and others built the first real databases on top of that idea. IMS in 1966, written for the Apollo program to track millions of parts on the way to the moon. It was hierarchical. Every record hung off a parent, like folders. Charles Bachman's network model allowed more links, but the principle was identical. You navigated. To answer a question, you wrote code that walked pointers, one hop at a time, in the order the designer had laid down years earlier. Here is the fatal part. The question you were allowed to ask was baked into the structure. A new question meant reshaping the data or writing a new program. Data and access were welded together. That weld is what the next generation broke.
1970. Edgar Codd, a mathematician at IBM, publishes a paper called A Relational Model of Data for Large Shared Banks. The idea under it is almost offensively simple. Stop storing pointers, store tables. A row in one table refers to a row in another by its value, not by its address on disk. And then the part that changed everything. You describe what you want, not how to fetch it. Select this, where that. The database decides the how. That is the separation of the question from the machinery, and it is why SQL has outlived every fashion since. IBM builds System R to prove it and invents SQL, later SQL, in 1974. Berkeley builds Ingress. In 1979, a small company ships a commercial version and later renames itself after the product, Oracle. By the mid-80s, relational is not a theory, it is the default. Orders, users, inventory, money. And that success is exactly what causes the next problem.
Because those databases are tuned for one shape of work, take an order, insert a row, update a row, read one customer by ID, thousands of tiny operations, each touching a handful of rows, each needing to be correct right now. That shape has a name, OLTP, Online Transaction Processing. Now finance asks a different question, revenue by region, by product, for the last 5 years. That query does not touch a handful of rows. It touches every row you have ever written. And the database stores whole rows together. So to read one column across 10 million orders, it drags every other column off the disk with it. It takes minutes. It holds locks. It fights the checkout page for the same disk and the same memory. In the 80s, the way you discovered this was that the monthly report ran and the shop stopped taking orders. So people did the obvious thing. They copied the data onto a second machine and ran the reports over there. That copy, once somebody took it seriously, got a name.
The data warehouse. The term surfaces at IBM in 1988 from Barry Devlin and Paul Murphy. Bill Inman writes the book in 1992. Ralph Kimball adds the design most people actually use in 1996, the star schema, a central fact table of events ringed by dimension tables that describe them, and a pipeline fills it, ETL. Extract from the live systems, transform into the agreed shape, load it in, usually overnight. 2 properties define this generation. First, the data is modeled before it is stored, schema-on-write. You decide the structure at the door, and whatever does not fit is cleaned or dropped. Second, it is built to be scanned rather than poked. Teradata had been selling machines since 1979 that split one query across many nodes. Vertica in 2005 stores by column instead of by row, so reading one column stops dragging the rest along. This works. It still works. An enormous amount of the world's reporting runs on exactly this. But it makes one bet, and in the 2000s, the bet stopped paying.
The bet is that you know the questions in advance, because to load anything into a warehouse, you must model it first, and to model it, somebody must decide what matters. That is fine for invoices. Then the web arrives. Now the data is click streams, server logs, application events as JSON, whose shape changes when a developer ships on Tuesday, images, audio, sensor readings. None of that is a tidy row, and nobody yet knows which parts of it are valuable. Ask a warehouse team to load 10 terabytes of raw logs on the chance it is useful next year, and you get a very reasonable no. Modeling costs people, and the storage costs real money, because in a classic warehouse, the storage and the machine that queries it are one product, bought together. So the data that did not fit the model simply was not kept. Meanwhile, 3 companies had this exact problem at a scale nobody else had reached, and they wrote down how they solved it.
Google, 2003, a paper on the Google file system. 2004, a paper on MapReduce. Together, they say something heretical. Do not buy one enormous machine. Take 1,000 cheap ones, assume several are broken at any given moment, spread the files across all of them, and ship the computation to wherever the data already sits. Yahoo builds an open-source version. 2006, Hadoop. HDFS for the files, MapReduce for the work. And the logic of loading flips completely. You no longer model data in order to store it. You dump the raw file in exactly as it arrived, and you decide what it means later at read time, schema-on-write. In 2010, James Dixon, then Chief Technology Officer at Pentaho, gives it the name. A data mart, he said, is bottled water. Cleaned, packaged, shaped for one use. A data lake is the lake itself. Everything flows in its natural state, and you take what you need. The name went everywhere, and then most of those lakes failed.
They failed in a specific, boring way. Nobody deleted anything because storing was cheap and deciding was expensive. There was no catalog, so nobody knew what was in there, who owned it, or whether it was still true. There were no transactions, so 2 jobs writing the same folder produced a mess, and a job that died halfway left half a table behind for the next reader to find. And MapReduce was slow and miserable to write. The result earned its own name, the data swamp. 2 things rescued the idea, and neither of them was Hadoop. First, in 2006, Amazon shipped S3, object storage, effectively bottomless, cheap, somebody else's job to keep alive, and crucially, separate from any machine that computes. Second, in 2009 at Berkeley, Matei Zaharia built Spark. Same distributed idea, but it worked in memory, it was pleasant to write, and it ran the same job 10 to 100 times faster. HDFS lost to S3. MapReduce lost to Spark. What actually survived Hadoop was one sentence. Storage and compute are separate things, and you should be able to buy them separately.
Which brings us to the question that started this. Is S3 a data lake? No. S3 is the floor. It is a place to put bytes. A lake is a stack, and storage is only the bottom of it. Above the bytes, you need a file format, not CSV, Parquet, columnar and compressed, so a query reads one column instead of every row in full. Above that, a table format, which we are coming to, and this is the layer that was missing for a decade. Above that, a catalog, so that something in the world knows this folder of files is a table called orders with these columns. Above that, an engine that reads it. Athena, Trino, Spark, DuckDB. And wrapped around all of it, permissions, lineage, retention. Take that stack away, and what you have is a bucket. S3 holding 10,000 unsorted JSON files that nobody can describe is not a data lake. It is the swamp, with a monthly bill attached. Storage was always necessary. It was never sufficient. Now watch the other side of the field, because the warehouse did not sit still. 2012, Amazon ships Redshift. Google has BigQuery, built out of its Droll work. And in 2014, a company called Snowflake comes out of stealth with the idea that mattered. They took the lesson from the lake, separate the storage from the compute, and built a warehouse on top of it. Your data sits in object storage. Your compute is a cluster you switch on for a query and off afterwards. 2 teams can run heavy queries at the same moment on separate clusters, over one copy of the data, and neither slows the other down. Suddenly, a warehouse is elastic, and you pay for what you actually run. It worked well enough that Snowflake's 2020 listing was the largest software IPO ever at the time. So by around 2018, there are 2 mature architectures on the table, and every serious company is running both of them. which is the real problem this whole story has been walking towards. The lake holds everything, cheaply, in open files, and it is where the data science and the machine learning happen. The warehouse holds the clean, modeled subset, and it is where the dashboards and the business intelligence happen. So you run a pipeline that copies data from the lake into the warehouse. Now you own two copies of the truth. They disagree, because the copy runs at 3 in the morning and something failed on Tuesday. Permissions are defined twice, in two systems, differently, which means they are wrong in one of them. Your model trains on a table in the lake. Your executive dashboard reads a different table in the warehouse. The two numbers do not match, and a person burns a week finding out why. You pay to store it twice, and you pay an engineering team to keep the copy moving. Everybody had this. Nobody liked it.
The fix is not a new database. It is a metadata layer, and it is the most important thing in this video that most people have never looked at directly, the table format. Netflix builds Iceberg in 2016 and hands it to Apache. Uber builds Hudi. Databricks builds Delta Lake and open sources it in 2019. 3 names, 1 move. Underneath, you still have plain Parquet files in a bucket, nothing exotic at all. What you add is a set of small metadata files beside them, which say, this table at this version is exactly this list of data files with this schema. That is the entire trick. And that one layer of indirection buys back everything the lake was missing. A write becomes atomic because it is not finished until the pointer swings to a new list. Readers keep seeing the old version until it does, so a half-finished job can never show anyone half a table. You can update and delete individual rows, which raw files never allowed, so a deletion request stops being a rewrite of the world. Schema changes become a metadata edit instead of a migration. And because the old lists are still sitting there, you can query the table as it was last Tuesday. Time travel. Warehouse guarantees on files you own in a format anyone can read.
Put that on top of object storage, point a decent engine at it, and the two system split stops being necessary. One copy of the data, in an open format, in your own bucket. Transactions and schema enforced on it. Your BI tool queries it, and your training job reads the very same files. Databricks named this in 2020 and published the paper the year after, the Lakehouse. For once, the name is doing something honest. It is not a new storage idea. It is the warehouse's guarantees unbundled from the warehouse's storage and dropped onto the lake. And the consequence that matters is about ownership. The data is in your bucket, in a format with a public specification. The vendor sells you the engine and the governance on top. If you leave, the tables are still readable. That is a very different bargain from the one on offer in 1990.
So why is Databricks the name on every slide right now? It is worth being precise, because it is not one reason. It is 5, stacked, and the last one is luck they happen to be standing in the right place for. 1. They came out of Spark in 2013, which means they owned the compute engine that replaced MapReduce. Everybody doing anything at scale was already running their code. 2. Their first users were data scientists and machine learning engineers working in notebooks, at a time when warehouses really only served SQL analysts. They sat next to the machine learning people for a decade before that became the most important seat in the building. 3. The Lakehouse move itself. They attacked from below with cheap open storage that slowly grew warehouse features, which forced the warehouse vendors to come down and meet them. Snowflake reads Iceberg now too. 4. The open source flywheel. Spark, Delta, MLflow, Unity Catalog. Give away the standard, sell the platform around it. 5. Timing. Large language models made unstructured data the asset. Text, PDFs, images, audio. None of that ever lived in a warehouse. It lived in a lake, which is the thing they had been running for 10 years. And they bought Mosaic ML in 2023 to sell the training that sits on top of it. As of the middle of 2026, that is roughly $6.9 billion of annualized revenue, growing around 80% a year, last valued at $134 billion. The story is not that they built a better warehouse. It is that AI made their side of the argument the side that matters.
So what is the actual trend now underneath the marketing? 5 things. First, the format war is over, and Iceberg took the neutral slot. Databricks bought Tabular, the Iceberg company, in 2024, days after Snowflake announced its own open catalog, and today, both sides read both formats. When competitors agree on a file layout, that layout has stopped being a product and become infrastructure. Second, the fight moved up one layer, to the catalog. Whoever holds the catalog holds the permissions, the lineage, and the definition of what a table even is. That is where the lock-in lives now, not in the storage. Third, the engine is becoming pluggable. The same files in your bucket, and Spark, or Trino,
or Snowflake, or DuckDB, or Polars can each point at them. That is the slow end of loading data into a system just to be allowed to ask it a question. Fourth, AI is the workload writing the checks. Vector search, embeddings, and agents that query your tables directly are being built into these platforms rather than bolted beside them. Databricks is pushing a serverless Postgres aimed at agents. That is where the new money is going. And fifth, the honest countertrend. Your data is probably small. DuckDB will scan 100 gigabytes of Parquet on a laptop faster than a cluster can finish starting. Most companies buying distributed systems hold less data than one machine could carry. That is worth knowing before you architect anything.
Which is the note to end on. Look at the shape of the whole 60 years. Every generation exists to fix one precise failure of the one before it. Navigational databases welded the question to the structure, so the relational model prized them apart. One relational database could not serve the shop and the report at once, so the warehouse split them onto separate machines. The warehouse demanded you know the question before you stored the data, so the lake stopped asking. The lake had no guarantees, so the table format gave it some. And running both of them cost everything twice, so the Lakehouse merged them again. The next generation will follow the same rule, and it will fix something that annoys you today. So, practically, under 100 gigabytes, use Postgres or Parquet files and DuckDB, and build nothing. Terabytes, mixed formats, questions you cannot list yet. Object storage, Parquet, Iceberg, and whichever engine you like. Heavy business intelligence, many analysts, hard deadlines, a warehouse still earns its money. All of that at once at real scale is the Lakehouse, and that is the invoice Databricks is sending. And the most expensive mistake in this field has not changed. It is building the lake when one Postgres would have carried you for 3 more years. If that was useful, subscribe. The short version and the written one are in the description.